Thank you, the organizers. I'll take less than that. In fact, I must thank Rajiv. A lot of my slides have now become redundant because he has covered a lot of these things. So, uh, well, I was going to show a lot of different slides on effect of climate change on the hydrologic processes. Some of them I will still show, but most of them I'll just uh, quickly go through because it has already been informed. So the overview of the talk, I think I wanted to start with what is climate change. That I will not do anymore. Hydrologic processes, we will discuss what processes are there which we are interested in, and how are they affected by a change in climate. Uh, Past trends, again, Rajiv has done a lot of uh, that past trend analysis. I will do a few maybe about maybe rainfall, not as much as temperature. Future predictions of climate and its effect on water resources. This I will take up a little more in details because there are a lot of uncertainties there, and I want to touch upon those little bit. And then some main issues, what issues are still remaining to be addressed. And I must acknowledge uh, Dr. Tripathi, the work which I am presenting. A lot of people have helped me, and Dr. S. N. Tripathi is here. My PhD student Chiranjeev is also here, and it's good that he is here because some of the questions he may be able to answer better. Ankit Dureja was my MTech student. He has now graduated. And then Ministry of Water Resources I thank because they are providing the funding for whatever climate research we are doing here. I mean, at least I am doing here. These lot of things have been already told, but I will probably mention that the frequency of severe floods in large river basins has increased, and average annual discharge of the rivers has also increased by 7% based on some 6 large Eurasian rivers. In India, as Rajiv already said, we have increasing trend in surface temperature, but no significant trend in rainfall as far as all India trend is concerned. Next slide. Okay, this I think most of you know. In this cycle, there are several processes, and what process is important depends on who you are. For example, if as a hydraulic engineer, I would be more interested in runoff, which is going to the river, so that I can harness that and supply water to the cities. If you are, let's say, an agriculturist, the infiltration and the soil moisture may be more important to you. So all these components of the cycle, there are different effects of the climate change on these cycles. Some people, since it's a cycle, we can start from anywhere. Most people start from the ocean, so there is evaporation because of the incoming solar energy, and then clouds, precipitation, runoff, and infiltration. The effect of climate change on these, now I think I should skip this slide because, yeah, yeah, this again, this is a past trend, so it just shows how the annual precipitation over the globe is changing, and the change is shown as like percent per century. The plus signs which are shown here say that at those points the trend is significant. So other places there is a trend, but it may not be significant, and there is a positive trend by different color and negative by different color. So it just says that annual precipitation over the globe is showing some trend which is not either increasing or decreasing. It's increasing at some places, decreasing at some places. In the last 30 years or so, this is the trend. But again, I will skip this because Rajiv has already shown this. This is some prediction about global surface temperature, and I'll talk about these scenarios because there is a lot of uncertainty about these scenarios. Low emission scenarios tell you that temperature will increase by 1.5 to 3 degrees. High emission 2.5 to about 5.8 degrees. In India, we expect, again, this prediction is very uncertain, so I'll go over the uncertainties, that there will be increasing trend in surface temperature, but no significant trend in rainfall will be observed as far as future predictions are concerned. But trends at some locations will be observed. This I will again remove. Now, effects of climate change on water resources. One thing is, as the air becomes warmer, it will hold more moisture. Evaporation will increase. Now, more moisture in the atmosphere typically would mean that precipitation will be more intense, and therefore floods may be more likely to occur. Higher temperature, intense radiation, this may lead to prolonged droughts. Then, in this, I would just look at the last 2 points. Seawater intrusion into the coastal aquifers. So, as the water level in the sea rises, the salt water will tend to come inland, and if you are pumping water inland, you might get brackish water rather than the fresh water. The last point should also be noted, because sometimes climate change may affect water resources or the hydrology in conflicting ways. For example, larger CO2 affects the plant physiology and reduces the transpiration from the plants. And increased temperature, larger CO2 causes increased temperature, but that leads to a larger evapotranspiration. So, these two are opposing effect, and what is the net effect, that will depend on lot of other factors. This I'll probably keep. The prediction for future is normally done based on the GCMs, and there are n number of GCMs, 10 to 15 GCMs have been used for a lot of studies, and this slide shows whether they agree or don't agree that precipitation will rise, which is on the positive side, or fall on the negative side here. So, if you look at the colors, you can see that at some places the models agree very strongly that the precipitation will rise, and some places they agree strongly, with not many places where they agree very strongly, but they agree strongly. For example, these two, they say the models agree that the precipitation is likely to decrease. So, that is what this slide shows, but these predictions, again I would emphasize that they are based on several GCMs, their comparison, and these GCMs are not very accurate as far as precipitation is concerned. So, I'll say this first point. Now, the variation in stream flow, as far as the IPCC report is concerned, it says that the variation varies, or the variation changes regionally and between scenarios. Now, between these scenarios, all of you are probably aware of these. So, these are the 4 scenarios which are generally considered as far as the SRES guidelines are concerned. So, we have, in fact, in our analysis, we have taken the A1B, which is technology is balanced, and then we have the economic emphasis and global integration. So, these I think most people are aware. But I want to touch more upon these uncertainties. So, IPCC report talks about lot of effects, and it also classifies what is the confidence level which we have in those conclusions. And if you look at this, there are a lot of conclusions which are with very high confidence, and most of these are in general. But if you look at the second point, the semi-arid areas, semi-arid and arid areas are particularly exposed to the impact. So, that has a very high confidence that the areas which are already dry will probably suffer more due to climate change. This again I will skip, because this is some projection of climate change over India. This is also some projection. This slide I just want to show. This is kind of summary of what we are interested in, how the precipitation will change. But note that this is 15 model mean changes in these variables: precipitation, soil moisture, runoff, or evaporation. So, these 15 GCMs have been run for scenario A1B, and their results have been summarized here as to what is the predicted change in the period 2080 to 2099. I don't want to discuss the details, but I want to emphasize more on the uncertainty. Now, a GCM, why is there a lot of uncertainty in several GCM results? In fact, there was a study which says that if you run 15 GCMs over these 4 scenarios, you have lot of variability in the outputs, and the model uncertainty is much larger than the scenario uncertainty. So different GCMs running for the same scenario will give you very different results. And why is it so? Because the GCMs are based on different discretization, different physics, and I don't want to go into technical details, but I will say here that a limitation of GCM, especially as far as the hydrologic variables are concerned, is that we don't have a resolution which is fine enough to take care of all the hydrologic variables. For example, a GCM may have a grid size of 200 to 300 kilometers, and any small scale variation in topography are not included there, because that whole block is given one characteristic. So that's why when we talk about hydrology, those small scale variations become important, and we need to downscale the results from the GCM to the local scale of interest. So this slide basically tells you what are various uncertainties, why the different GCM results are different, because there are fundamental equations which are taken differently in different GCMs. When you solve those systems, again you are taking different methods, and then discretization is of course different for different GCMs. So this causes a lot of intermodal variability, which we are still not sure how to take care of. And then we need to downscale. That means we need to convert the GCM results to a scale which is suitable for our purpose, and for that we need a downscaling for the GCM result, downscaling to the local scale or the regional scale. And for that there are basically two methods. One is based on statistical downscaling and one is dynamic downscaling. So the idea here is that once you get the GCM result on a coarse grid, let's say 300 kilometer grid, you want to downscale it to a 50 kilometer or even less, because that is where we want to run our hydrologic model, at which scale it will give us reasonable results. Statistical and downscaling and dynamic downscalings, they basically employ different techniques. A statistical technique relates some of the variables which can be observed or which are predicted by GCM to our quantity of interest, for example, precipitation or temperature. And we assume these three assumptions which are listed here. We assume that we know all the variables, all the predictors which are affecting our variable of interest, whatever relationship they hold, because the relationship is based on the previous data. And what we assume is that whatever relationship was there, it will hold in the future also. That may not be a very correct assumption. And dynamic downscaling is based on GCM type of models applied at a finer and finer grid. So typically we will be using some kind of regional climate model for this downscaling. But downscaling itself is also uncertain. From going from GCM to RCM or downscaling the values, again has lot of uncertainties. Whatever results we get from the downscaling, we should not think that it's all perfect, because there are a lot of uncertainties again. Parent GCM has uncertainty, the scenario storylines, they have different uncertainties, downscaling methods have their own uncertainties, domain of influence, because we are not sure when we downscale, we take a smaller domain, and whether any effect of the process in that domain is felt outside or not. So these are some of the limitations which cause uncertainties in our results. For our hydrologic modeling, these are the important variables which we need: topography, land cover, slope, soil type, and groundwater information. This is the method which we are using here for downscaling. This is a weather research and forecasting model. This will help us in downscaling the GCM results. And if you see this nesting, this is what we have been trying here, telescopic nesting. So we run it for a finer and finer grid. So we run the outer grid, take the boundary condition from there, run the inner grid with those boundary conditions with a very fine grid, and we go on to our area of interest, which is in this case this area number 3. So telescopic nesting is what we have used in our simulations. And I'll skip a lot of these things. I want to show you one. Uh, okay, uh, let me show this. For modeling, for hydrologic modeling, we need these static fields or the properties of the grids, which will have significant effect on our simulations. And for India, we have these fields available. I'll show you one sample. Uh, so this like topography, land use, leaf area index, and soil type map, these are available for the country. And when we input this in our hydrologic model, we get the results which we want. One of the major drawbacks of hydrologic modeling under climate change is our inability to predict extreme events. So this is what we did. I will not go over details of this, but there was a cloud burst in Leh area in 2010, August 2010. And since most people say that extreme events cannot be modeled or are not easily modeled, we took this up as a challenge and said that, okay, let's try to model this cloud burst. Given the condition a day before that, can we manage to simulate this cloud burst to show that there's so much rainfall actually occurred on that day? And since I have only 1 minute left, I'll just show the results. So I will not go over the grid details. So this is the rainfall, which TRMM is the measured rainfall and simulated rainfall. Now domain 1 is the outermost domain, and what I want to show here is that outermost domain doesn't show very good matching with the observed value. As you go inside, domain 2 is nested within it, the predictions improve, and domain 3, which is the kind of centered on Leh, our smallest grid size, was showing a very good match with the maximum rainfall which was observed at Leh. So we were able to simulate this very well. And the paper which we sent recently got rejected, so I think we must have done something good. But I think the comments were quite encouraging, and it looks. So there was one more case which I had to discuss, but let me stop here. I'll not go further. Thank you.